Hello everyone, welcome back and happy Pride Month. Today what we'll be building is our interpreter. But first I'd like to explain some of what I did off camera. So what I did was I built this thing called raw. And raw basically what it does is it just takes in a byte slice and then gives us access to the underlying structure through like accessor methods as well as iterators and whatnot. Some of the things that might be more interesting to talk about that I also built out some of the interpreter. These are more or less just under background data structures like a bytecode table and function table. One of the things that we also need, which I didn't put in the code, is a string table. And the string table is actually kind of interesting in how it's designed. And honestly, it probably wouldn't have been cool to put on camera. But to summarize, basically what we do, we have these things called slabs, which are just byte slices. And they store a certain amount, in this case 64 kilobytes. And so what we do is whenever we get a new string, we load it into the string table. And then we add it to the slabs. And basically once the slab fills up or gets to a point where we can't put anything else in it, we will then create a new slab and put the string in there. And we also deduplicate with this hash map. And since we're just putting raw data in, we could just use a static thing because we could basically say it's a static reference. Because the slabs should never be deallocated because they should always live for the lifetime of the program or lifetime of the interpreter. And so that is one of the things that is kind of cool, but for now we'll be working on the link here, but for now I'll put it on raw so I can reference it. But here we're building the link here, and so because what we need to do for the link here is when we take our module files, they basically just say like, oh, I'm calling function foo, but function foo is not exists within the module, and so what we have to do is be like, all right, module A, which wants foo, needs to figure out where foo is, and we basically load everything statically, and it's like, oh, foo's in module bar, and then from bar just gets dumped in, and then we link everything together, and then we start executing and we call foo and it works out fine. So I wrote a quick function that it takes in a start module because we want to pull the start function or from a certain module, and we want to collect as many errors as we can during the linking process. And then we have this link module which just does an individual module. Now I just need to add something. Which is we need to use create a new string table builder and pass this into link module, which I shall put here because it's actually kind of important. Strings. Oops. And so I need string table builder. Alright, so the first step is we'll keep the unimplemented there just so then it doesn't yell at us when it's like, hey, you haven't returned anything. It's like, yeah. So the first thing I want to do is we want to pull in the module string table. And to do that, we'll do module and get the string table. And so what I want to do next is go and get the start function string index, and that's what we'll be returning. So I'll do let actually no, this is fine. If module dot string index is greater than 0, meaning that it's not null, we are going to take a module dot, or not, I'll take the string table and index into it our module dot start function string index, and that will give us a string Why is this complaining? Where are you, string table? Oh, it needs a U size. Yeah, I think I know why, because it's internally used. So we get that, move that, and then we do, oh, so actually, this should be some, this should be none. And then we then just look that up at the end, which we could do later. For now, we need to we might as well load the string in while we're here. So we will go strings dot add string about string as bytes, and then I'll dump it into the string table. And so now the next step is we want to go through each section. So I'm going to do for section in module dot section iterator. This gives a table entry. I want to match on section. For now, we don't handle any other section except for a few. So what we'll do now is we'll do let's this will be helpful. Table entry, and all we care about is function. And then, oh yeah, we don't low, we want raw. This now should be unnecessary. And then the other thing we want is the bytecode table. And then we need to do a let. We need to create the function table. And then same with the bytecode table. And then this should be function table equals some function table bytecode table. And then it's gonna be like, we haven't read that yet, and then we'll do next, we'll grab the other tables when we need them, but we'll do a let function table equal raw bytecode. No, raw bytecode. We want bytecode table. Patch raw function table and raw. And technically these may not exist in a module, theoretically, but it would be kind of weird for them not to. So, I don't know. Basically, we want some function table and some bytecode table. I just want to return the 2. And then otherwise, let's do handle that should. Why is this complaining? Oh, I know why, because I missed a. There we go. And now that we have these, I think we'll just do a for function in function table dot function iterator. And we'll do a. What can we do on a function? So we're going to create a function. So what we want to do is I have a thing up here where I have a function and want to create this. So actually maybe we'll open this over here. And so we need a name. So name equal string table dot index the function dot name as usize, and then we need the bytecode for it. So code equal bytecode table dot, and of course I don't index it because that would be convenient. I think the reason why is because why do I do it that way? I think it's because the I should add it. It shouldn't be that hard. It should probably be in there. I can do it. There we go. Next. Yeah, let's keep it usize. And then let's give us a bytes u8. Oh, I just realized something. I know why. Okay, never mind. We don't need that. We don't need that. I'm gonna be like, why do we not need that? Well, it's because it's actually quite simple. We actually need to link the bytecode. We have actually we need to open up. I'll open up here. We actually have a new bytecode set up, which I put in this dot comment. And it looks about the same, except for there's a few differences. which are that or calls a function index. And so what we need to do is we actually need to resolve all functions. And then after we resolve all functions, then we can start being like, all right, we iterate to the bytecode table and start pulling out stuff. So let's leave that there. So create a function. We need to load the names in. And so look at the function table as a useful thing, which is function table dot not function table, we want functions dot add whole, which will basically give us, put name in there, and what it turns is an index into the function table. Why is it? Oh, it needs it to be static. Okay, that's fine. So let name equal strings dot add string and we need to put name as bytes, and then now it's the wrong type, which now we need an index string table, but I, in my infinite wisdom, forgot to provide a method to the string table that lets us just index it. So no. Index string. I actually just call it index. We don't need the be itself, it could be that. And this will have to be const because, oh, not const, static, because otherwise we'll run into issues. So this needs to be a static str, and then we do a out equals self table dot not index table, but index internal, which then we just put an index. Oh, I just don't need to do that. Okay, I'm smarter than I remember being. And so this will now we can just go name equals strings dot index name. Now we have a static string, and now it works. Yay! And so add whole says is basically like, hey, we're gonna say that this function exists, but we haven't interacted with it yet. So yeah, so now what we'll do is, what do we do? So we'll loop through every function, add them, say that they exist. And then we probably want to collect the bytecode indices, so then we can add them. So func names bytecode, do it with capacity, and function table count will give us exactly what we need, except for this needs to be a use size. And so, and luckily, even though add whole does return an index into the table, we don't actually care about that, simply because we can access it by name. So now what we do is do func names bytecode push. I figure might as well store the name just to keep it around, and then do function dot. I I have a better idea. Function names. All right, so function name is func, and so we'll just include the function. Why aren't you working? Oh yeah, because I renamed it. All right, so now we have that. Then we want to do is loop over everything in bytecode. So for this function in bytecode table dot iter, which will just give us an iterator over slices. So with that in mind, we want to create a new function which is going to be called link bytecode, which is going to take in a U8 array. No, code, and then we probably want the same parameters here. Oh, and that we probably also want the string table. Yes. That's not where I want it to go, but okay. So I want that. And so we will need the string table, which is a reference. The string. No. To raw string table. There we go. Want that. So we could reference strings. And so what we'll do is create just an iterator. Just code dot. Yeah, we just want an iterator. And what we want to do is match on the bytecode, and then whenever we find it, look up the right information and put it in. So I'm actually going to open up high here, so I can remember what all this is. And plus the bytecode format will be ever so slightly different. So actually it's while some byte equal iterator next. So what I want to do is do a match on the byte, and if it's 0, we know that this is actually we need one last thing. That we need a vec of U8, and we need to do linked bytecode is a vec. Let's just say it's about the same capacity as len. I think that is reasonable. So we'll just return linked bytecode. Linked bytecode. Actually, what? No, that seems reasonable. Actually, do we even have to return it? Yeah, let's return it. Just keep life easy. And so what we do here is we know this is push just a I8. So what we need to do is just change how the push works. So length bytecode dot push 0 because it's still going to have the same byte. Actually, the operand is going to never change, or rather the code point will never change, but the value will. And so what we need to do is get the operand be something like what was I going to say? I think it's a constant, so let's do iter next. Else, not thinking about it, this is I think your error. So let's add a so this can actually fail. And look, I have a nice type def to wrap it around. And so we return error, like your error, unexpected end of code. And then what we want to do is do linked bytecode push the constant. Don't want to double dereference it. And then for this, we're actually going to change it to all constants are the same width. So we're going to push on 8 zeros. Oh, not 8 zeros, 7 zeros. And basically, what it's going to do is when we actually execute the bytecode, we'll just read a full U64 out of the bytes and just push it on there whenever we hit any of these push instructions. And that way, the logic will be a lot faster and simpler. Because when we actually go to execute it, we actually don't care what the values on the stack are. We just trust that the operations will be sane. And the only way to do it is ensure that if everything's the same width. Otherwise, you'll get to nasty issues. Plus, there's probably some weird optimizations. And so now, one, which is pushing a U16, or just a 16. Let's do byte 1, byte 2, and so So this is now pushing U32. No, this needs to double every single time. And so with that, we will build out the linker some more. I'll go on to the next one. And this will be a 64. So we will need to R5, R4, R4, 6, 2, 3, 4, 5, 6, 7, 8. R6, R7, R8, and then we actually want to just yoink these two. Put them here. Change that to 4. Yes, 4, and this the 5, because what we're gonna do, that's basically the same as these two, that floating point numbers, and then for basically 6 through to 7, 8, 8, we do nothing. So this will be pop, dupe, swap, and then we're going to get load local, which is 9. And I'm going to sanity check the conversion. Yes. All right. And so 9 will load a local. Index. And so we will add the index, and then we'll just add this for, because this also have this is like the same sort of instruction, because it's storing, then create up value. It's kind of the same story. Maybe we could do so it'll be 9, 10, 11, 12, 13. And put load/store local value, actually create load store or up value. Just to reduce duplication of code, and then for this is 14. This is a load global. And so we actually will need this. Actually, no, we'll need this to reconstruct the string table index. So it'll be byte 1, 2, 3, 4. And so that will not work because we need the dereference though. And then with that in mind, we now need to access the string table. Let global name equals string table dot index as size. That will give us a global string. And then we'll I just go down to name, do strings dot strings add string and do global name as bytes. That gives a thing. I'm gonna do let underscore name equal strings index name. That'll give us a global string, and then this is where we hit a roadblock because we haven't implemented yet. Because what we need to do now is get the global index, use the global table index and put this in here. But we don't have that, so I'm gonna do is add it to do. So it'd be load global table with entry, and we'll need to do this by going to the global table and accessing it, but we haven't done that yet, so we'll continue with basically probably the same logic as load global and store global. So we'll include that. So now we're on 16, which will be all right. Arithmetic. These are going to be nearly identical. So 16, 17, 17. The skip. Actually, technically, they're all the same. Other than they could be invalid ops for the floating point numbers, so I think it's fine. So let's see, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. Yeah, 35. So let's see, LU operations plus ops. And how do we, I forgot how we convert these into bytes. Width just gets converted into binary as well, which those are just U8s. All right, that's fine. So we just need to pop off 1 byte and call it size. And then we'll just do bytecode.push and dereference size, and then we've basically done a lot of the bytecode entries. And what's next is complement, which nothing but complement technically also fits. So then I guess logical and to logical not. 38. So we'll put and or not basically is a boring one because we just pushed the stuff on. Oh wait, there we go. And so now we do comparison, which comparison's basically the same thing for all intents and purposes. So we'll basically yoink that code. So 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54. Comparison ops. I cannot spell. Are basically the exact same thing as this, which is great. And then now for 55, we now have two of them. So we have a 55, 56, 57, 58, 59. All right, 59. Conversion ops, which is basically these, but doing size 1 and size 2. And then we have all the conversion operations. And then we do 60, which is another size thing, so that is what we need. It just flips the bytes. Which is this. Why is it complaining about this? Oh, I know why. And then now we get to the more control flow one. This is start block, which honestly, start block and jump can be considered about the same. So we need to basically yoink this code here. Like that, we're going to just skip adding these back. And some might argue that, like, oh, maybe we keep everything aligned, and I'm like, maybe, I don't know. If that slows it down, then that's an optimization that can be taken later. Now we have, need to add, nope. I'll just yoink this since it's going to be pretty similar. And this is going to be jump if. Should be on 63. And just 63. And I'm going to be especially lazy and just duplicate the code. Not great, but it's fine. Okay, and 64 is where things get a little bit complicated because it's a match. It means it's variable length, which is not great. So this, we're going to do match. The first thing we need to do is, if I recall correctly, we just read a U32. Which word? I know there we go. Read that. So then we can get a count. And with that, we now know how many bytes to iterate over the gather. So we're gonna do for in 0 to we're gonna do size. What is size? Well, let size equal count times size of a U64 and a size of, oh, that should be a plus of a I32 as we defined it in our code. And oh, it's because this needs to be a U size, and with that we will now be able to iterate over the limbs. And what we need to do is do linked bytecode dot extend and do count dot as le bytes. Was it 2? That's not count. It's 2 le bytes, isn't it? Yes. And then while this happens, we yes, okay, this is good. Is we just do just yoink this. Byte. And what we're going to do is do like bytecode dot push byte. And then what this will do is it'll just start chunking. It'll get every single byte. It'll get every single portion of the U64 and the I32. Next is int match, which could get sketchy, and so I will skip that. Because it's kind of the same thing. Because what int match is, it's a bit match on a variable length integer, which means that this static U64 can be variable length, which is not great. So we'll have to deal with that, but I don't feel like that. Also, I think this video is probably getting really boring because it's just me hacking away at a lot of code that is kind of redundant and kind of repetitive. So I'm going to leave it here and work off and finish most of this off camera. And then on the next episode, we can actually build the interpreter. So see you guys next time. Goodbye.